Hi, I am Robledo and I'm going to do a presentation on my PhD thesis labeled Physics-Informed Neural Operators for Aerodynamic Surrogate Modeling, Enhancing Generalization and Robustness in Aircraft Flow Prediction, being my supervisors both Rodrigo Castellanos y Carlos San Miguel. My thesis is motivated by the ever-growing and self-maintaining cycle of data availability, model complexity, and cost. Surrogate modeling first surfaced when engineers or scientists had a series of experimental or tabular data where tendencies had to be extracted, as seen in the images introduced. However, due to the lack of computers, the amount of data available was extremely low, and mostly limited to point clouds, which led to the creation of the most simple surrogate model, the linear regression through least squares, as seen in the graph I introduced. The appearance of the first computers caused a significant reduction in the cost of obtaining more data. So, instead of focusing on fitting all the available data, we focused on more complex problems, leading to the appearance of classification algorithms such as decision trees or k-neighbor models, as well as more advanced techniques such as the principal component analysis or PCA. Moving on to more recent times, at the beginning of this century, neural networks arose as general nonlinear surrogate models. Since then, it has been a continuous race to increase computational power so we can have larger and more complex models, allowing to fit more data at a cheaper price. As a reference, a study by Stanford reports that model training time is doubling roughly every 5 months, while the dataset size is doubling every 8 months. Also, consumption for training these models is multiplying by 5-fold every year since 2020, which is quite a lot. So, in other words, engineers and scientists have always focused on doing more with less, or can also be said that the objective has always been to optimize information usage, which is the final and ultimate objective of my thesis. I have been working towards this objective for some time, and I have approached it from a different number of perspectives. The most promising ones where I obtained some results include adaptive sampling or greedy sampling, which focuses on efficiently sampling some points within a parametric domain in order to efficiently build databases, minimizing the computational resources required. For this, I had to study conformal prediction and design of experiments, and I'm hopefully submitting these results at the end of the summer. Furthermore, I also studied a multi-fidelity framework for airfoil shape optimization, where I embedded the multi-fidelity framework within the optimization process, and through an automatic high-fidelity triggering mechanism, we minimize the computational resources required without compromising solution quality. And lastly, a novel technique we called soft physics, which will be the center of this talk and will give more details later on. Following with the state of the art for this last topic, my thesis builds on a recent family of neural networks called neural operators. Instead of the traditional input-to-output regression, these architectures aim to map between infinitely dimensional function spaces, which should translate into much better generalization, or that's the idea at least. Some recent examples include the implicit neural representation as the one presented by Catalani and co-authors in 2024, or the geometry-informed neural operator of Lee and co-authors in 2023, designed for problems where geometry itself changes. Others push it even further, towards large pre-trained foundation-style operators, such as the network of Herde and co-authors presented in NeuroIPS in 2024. But there is a catch. In practice, no one really agrees on what makes a neural network a genuine neural operator. And almost all these gains and error reductions come from increasingly complex and expensive architectures, as can be seen in some of these images. This is precisely the trend I want to avoid in my thesis. Apart from neural operators, a second major idea for my thesis is the physics-informed neural networks, or PINs, which impose known governing equations to improve accuracy while maintaining and respecting known physics. The drawback is that PINs require a great deal of loss tuning, as well as a huge cost for the training process. The approach I want to follow keeps this PIN philosophy, bringing physical insight into the architecture and the training, but combines it with a simple neural operator without overcomplicating anything. In this case, I chose the DeepONet for its mesh-free nature, which is very suitable for fluid mechanics applications and aerodynamics. I should also stress that pins are not always possible. Sometimes the data available online does not contain all of the required variables for the equations, or there are simply no equations for the target quantity. as in the example coming up next, surface pressure prediction from 2D run simulations. This brings me to the approach we call soft physics, developed together with Domenico Borsacchiello during my stay at École Centrale de Nantes. In soft physics, there are two main ideas. First, we want to leverage analytical relationships instead of full PDE models, and second, these relationships do not necessarily have to be included in the models used to generate the data. It sounds a bit weird, but will become clearer upon the application I will present later. Ideally, these two conditions and ideas should be more stable and computationally cheaper than the PINS approach that are being employed nowadays. This idea was first implemented in a surface prediction problem. We have a dataset where we have a different number of airfoils with different shapes, as can be seen on the top left. And for each of these shapes, we have the surface pressure coefficient. The idea is that given a specific shape, we obtain the full CP profile. For this, we are using a DeepNet-like structure where we have two branches and one trunk. We feed the geometrical information, in this case the NACA numbers, to both branches, and the specific coordinate where we want to predict the pressure coefficient to the trunk. In this way, combining the outputs of the first branch and the trunk, we obtained a proxy we call phi that, after going through an analytical layer, we obtain a proxy for the potential solution of the pressure coefficient. And combining the output from the second branch with the output from the trunk, we obtain a correction factor we call the delta. Combining the potential proxy with the delta, we obtain the final prediction. And as you can see in the plot on the left, the soft physics approach clearly improves the predictions. The error distribution shifts lower and becomes narrower. To check that the network is not simply combining the proxy for the potential and the delta and doing whatever it wants, we compare this intermediate solution of the potential CP with the actual CP obtained from a potential flow model. And as can be seen in the lines represented by orange and purple colors, the agreement is quite good, meaning that we are actually obtaining a proxy or an intermediate solution that somewhat follows potential flow theory without fully forcing it, giving the model more flexibility than if we use the potential flow model. I would like to emphasize that no potential flow data was used in the training, and as such, this is not a multi-fidelity approach. We just leveraged the potential flow analytical solution to condition the training in order to improve prediction accuracy. Building on that idea, we moved to a more demanding dataset, 3D surface pressure over a fixed wing geometry, spanning from incompressible to transonic regime across a different number of angles of attack, as can be seen on the left of the slide. We kept the same procedure as previously, but the main difference now is that instead of having a 2D potential flow proxy, we have a 3D panel method proxy where we predict the vortex intensity on each of the panels. And this is being tested as I am speaking, but the preliminary results are quite good. Here in the image I just showed, the red star represents the direct prediction via DeepNet, and the rest of the points are soft physics models with different weightings of physical losses. And as can be seen, towards the left and up is better performance, and almost all models except two are better performing in both accounts of the lift coefficient prediction and the absolute error, the average absolute error. Although soft physics is what I am currently working on, and I would like it to become the core of my thesis, I was already involved in research before I started my PhD. So I would like to close by sharing a few milestones from my first year and a half. These include a PhD summer school I attended on July 2025, a conference I attended on Lahti, Finland on September 2025 called Eurgen, and finally on December 2025 I published my first paper, which was from my bachelor thesis. On March 2026 I started the international stay I am currently doing. On April 2026 I published the second paper on experimental aerodynamics. On May 2026 I published my third paper based on my master thesis. And lastly, on May 2026, I uploaded to archive the fourth paper and hopefully submit it at the end of this week. So thank you for listening, and if you have any questions, I will be glad to answer.